Hi all. In our last example, we worked on average velocity, and then we worked into finding some instantaneous velocities numerically and graphically and with technology. And now we're going to work on the pieces of how you would do that algebraically. Again, the instantaneous rate of change part, we're wading into it a little now. We will formalize that a little bit more over the next couple of assignments. So if it still feels a little hazy, that's okay. But just try and start getting that general understanding of what we're doing. In particular, this question asks us to use that same position function we've been using, but now we'd like to find the most simplified expression for the average velocity on the interval 2 to 2 plus h. So those are t values, that's t equals 2 to 2 plus h, which means we're basically being asked to set up a difference quotient. We need s of 2 plus h minus s of 2 over 2 plus h minus 2. And notice on the bottom, those 2's are going to drop out. We'll just have the h left over. On the top, we'll need to plug back in to our function, 64 minus 16 times 2 plus h minus 1 squared. And then minus s of 2, I'm just going to do a little scratch work for that, 64 minus 16 times 2 minus 1, so 1 squared, which means we have 64 minus 16, or 48. All right, so there's our difference quotient set up. We're going to need to do a little bit of simplify. In here, I'm getting h plus 1, so we need h plus 1 squared. I think I'll work on that next. So I see 64 minus 16 times h squared plus 2h plus 1. So first big place for a common error that I see is distributing that exponent instead of FOILing it out. Remember that h plus 1 squared means h plus 1 times h plus 1. So we have to multiply that whole thing out. We can't just do h squared plus 1 squared. And then we have minus 48. I guess I could have combined that. We'll do that in the next step. Okay, so I see a 64 minus 48. That gets us actually back to 16. And then I also want to distribute the 16 through the parentheses. So minus 16h squared minus 32h minus 16. And that's all over h. We can drop out those 16. 16 minus 16 is 0, so that's going to drop off completely. And remember, when you're simplifying difference quotient, your most important goal is to try and cancel out that h in the denominator, that lone h. It doesn't mean all h's are gone. It doesn't mean there's no h's in the denominator at all, but that lone factor of h should be gone. To cancel it, I would need to factor. So I will remove an h. You could also remove the negative 16 if you'd like to. That's entirely up to you. It might look a little bit nicer. But mandatory is that that h gets factored out so that we can get rid of it. So I'm getting negative 16h minus 32 as my average velocity expression. All right, so we want to get a little bit of a handle on what that's actually telling us. So that's what this next question is for. We would like to figure out, based on what we just did, without having to go back and do this from scratch, what is the average velocity on the interval 2 to 2.5? And what we did already was 2 to 2 plus h. So basically, the 2 plus h has to equal the 2.5, which means the h has to equal 1/2. So we've really built a formula right here that says if you want to start at t equals 2 and go h seconds, it could be before or after. It looks like after, but if h is negative, it would actually be before. So I'm going to say after, but it could be either. So starting at 2 seconds, go h seconds after that, and that's your time interval. And this will tell you the average rate of change. So the average rate of change from 2 to any other point, basically. So we can just go right back to that formula and say, okay, well then the average value from 2 to 2.5 will be negative 16 times 0.5, which is our h value, minus 32. Half of negative 16 is negative 8. So negative 8 minus 32 gives us negative 40 feet per second. So we now have a formula that will do this for us. As we were building our table up above, this could have been really handy when we needed to calculate like 6 of these average values. Okay, so there's our average value talk. And before we jump into instantaneous rate of change, I just want to point out one more time that this formula that we created says that starting at t equals 2, you can pick the length of your time interval. So h is the length of time, and this will give you the average velocity. So the last part of this, and again, this is the part where we get just a little ahead of ourselves, but we'll wrap it all up in the next 2 sections, is can we now use that average value formula that we found to estimate what the instantaneous velocity at t equals 2 is. So this again is saying, okay, we want our second point to get closer and closer and closer to our first point. So we did a 2 to 2.5, maybe we want to do 2 to 2.1, and then maybe we want to do 2 to 2.01. And notice that 2 to 2.1, that's an h equals 0.1. 2 to 2.01, that's an h equals 0.01. And the idea would be the smaller we let that time interval get, that h value get, the better estimate of instantaneous velocity we will be getting. So really, in our average value formula, we want to let h get really, really close to 0. And that formula, we can do that easily. So when we let h, we can let it be 0 even. That's not always the case. Sometimes we have to be a little bit careful. But when h is 0, we're just getting negative 32 feet per second. So it appears that our instantaneous velocity at t equals 2 should be negative 32 feet per second. So we are basically finding the derivative. The only thing we're missing is a little bit better version of this notation. I've kind of started it for how do we say we're letting something get really, really tiny, infinitely small, or we might want to talk later about letting something get infinitely big or anything in between. And that notation is limits. So that's what we'll do next. And then we'll come back and we'll wrap this all up and do a formal definition of the derivative and then calculate those algebraically without this kind of working our way up to estimating it.